Hey guys, this is 8.3 composite functions. It's a topic that you should have seen at least briefly in grade 11 math, but fits into our combination of functions chapter as well because it is a combination of two or more functions, and you'll see how that works in a minute. I wanted to start with this little Plix interactive challenge just to show you an application of composition of functions so you can see what might motivate learning this topic. So we're starting here with a puddle of water that's forming, I assume from rain, and it's expanding at a certain rate. The radius of the circle is expanding at a rate of 0.5 t according to the function that we're given here for radius in terms of time. And if we pull out this little red dot here, we can see as the time is increasing, so is the radius of the circle and so is the area of the circle, which we should know from our grade 9 formula depends on the radius. So the area of the function depends on the radius of the function. And we'll get a reminder of that formula in a minute. So let's challenge ourselves here. At 5 seconds, what is the radius of the circle? And so we just have to pull this little dot in until it says t equals 5 seconds. And the radius is 0.5 t, or we didn't need to do that. We could have just used the formula. 0.5 times 5 is 2.5 units. So that should be the answer, yeah. Next question, what is the formula for the area of a circle in terms of its radius? So as I said, it's something you learned in grade 9 and obviously have used multiple times since. And so of course you should remember that it's pi r squared. Not to be confused with the circumference of a circle, which is 2 pi r. So make sure you don't confuse those. Next, this is a little bit more challenging of a challenge question here. So the radius of the puddle is 0 when time is 0, makes sense, but expands at a rate of 1/4 unit per second instead of 1/2 unit per second. So what they're saying is this function here, r of t, instead of it being 0.5 t, would be 0.25 t. And the question is, by what factor does the denominator of the resultant composite function, a of r of t, change from that in the opening scenario? So before we can answer this, we need a little bit of context. So let me flip over here to my definitions. A composite function, and I'm going to go through the mathematical definition after this example, but just the meaning of a composite function is that the value of a composite function depends on another function. It is formed when a function is evaluated at another function. In other words, one function is substituted into another. Okay, so let's see how that works for this example, and then I'm going to show you how it works in general. So in this example, originally r of t equal to 0.5 t was the function that we were given that relates how the radius of the circle expands relative to time. And we know that the area of the circle depends on its radius and is described by the function pi r squared. So a of r of t means I take the function r of t and I substitute it into a of r wherever there's an r. So that's why I've highlighted r of t here in red. That's the function that I'm substituting into a of r. And so that would be pi of 0.5 t all squared. And when you simplify that, it comes out to 0.25 pi t squared, or pi over 4 t squared as a fraction. But in this challenge number 3, what they're saying is if that relationship between radius and time was instead described by 0.25 t, then how would that change the denominator of this function here, a of r of t? And so we take our r of t, let me highlight it in red again here. It's now 0.25 t. And put it inside a of r, wherever there's an r. So we substitute in for r in pi r squared. Simplify it, and we get pi over 16t squared. So challenge number 3 asks us, how has the denominator of this function, a of r of t, changed relative to this function, a of r of t? So let's go back to the challenge. And our choices are, by what factor does the denominator of the resultant composition function, a of r of t, change from that in the opening scenario? Well, in the opening scenario, when r of t is 0.5t, it was 4, the denominator. And now, as we see, the denominator is 16, so it's changed by a factor of 4. All right, that was a little bit challenging. Well, appropriate since it's called a challenge. Let's see what the next one is. Substituting the function r of t for r, what is the composite function a of r of t? So in general, if we substitute the whole function r of t equals 0.5t into the area function, which is pi r squared, what does that function look like when it's simplified? So that would be pi times 0.5t all squared. So I believe we've already done this over here. Let's just go back and have a look. Yeah, whoops. Right, so it came to pi over 4t squared. So that should be this one here. Yep. All right, last one. Open discussion. You find a puddle and measure its area using the composite function you found in the opening scenario. So that was this one here, the pi over 4t squared. A of r of t equals pi over 4t squared. How could you solve for the time it took for the puddle to form, or for the radius? Okay, so let's have a look over here. So how could you solve for the time it took? You know what? I'm going to leave this for a minute, and maybe we'll come back to it, because before we do that, let's look in a little bit more detail about what composite functions actually are. So first, let's just look at the notation. This is the notation for composition of functions, f composite g of x, and it's a little circle here in the middle between f and g. Little circle, not a dot, because dot product actually means something else in calculus next year, but a little open circle, and it's in the middle between f and g. So f composite g of x equals f at g of x, which reads f composite g of x equals f of g of x, or f at g of x. Either one is fine. It is formed when g of x is substituted into the function f of x wherever x appears. And this is really important. Always go from the inside out. Super important. I'm going to highlight it in red. Okay, before we do a couple of examples on that, let me show you a visual aid for composition of functions here. This is the function machine composition. So the composition of two functions f and g is the function formed by taking the output of the function g and using that as the input to the function f. If we represent both f and g as function machines, the composition would look like the following figure. So let me just emphasize that if g of x comes first, if the function machine g comes first, that means we're looking at f of g of x, because we have to always go from the inside out. Okay, so let's just look at the machines for a minute. So what's happening is there's an object going into function machine g. That object will represent a value, and if g was a mathematical function. Out of function machine g comes a different value. In this case, it's a cube. So function machine g has changed a circle into a cube. Okay, that's what the function does. When the function comes out of g, it then goes straight into function f. Notice that the funnel for the result of function g fits the shape and size of this cube. If it didn't, then this composition of functions wouldn't work. Mathematically, that's analogous to the range of the function g has to match up with the domain of the function f. Okay, I'll talk a little bit more about that after. So the cube from function g goes into the function machine f and comes out as a different shape altogether. I can't see how many sides it has, but a lot more sides than a cube, right? So function f has done something different to this cube, and now function f spits out this multi-sided figure, which is totally different than the circle that it started with at the beginning of function g. Okay, so this is meant to be a geometrical analogy to the composition of functions. You start with something, a value, goes through one function, becomes something else, goes through the next function, which it has to be able to fit into, and comes out as something different again. So let's go back to our mathematical discussion of it here. And let's look at example 1 here. So we're given f of x equals x squared and a second function h of x equals tan x. We want to find the composite function f of h of x. That is equivalent to f at h of x or f of h of x. And what that means is take the function h of x, which is tan x, put it inside the function f of x, which is x squared, wherever there's an x. Okay, so you just substitute it right in for x in f of x. And the composition of the two functions gives the function tan x all squared. So that's our result of the composition of functions f and h. Now remember that the order matters. You have to go from the inside out always. So you take the inside function, you substitute it into the outside function, and then you simplify if you can. Okay, one more quick example here. We have f of x equals x plus 2, g of x equals x squared plus 5x plus 6. So we want to do f composite g of x, which is equivalent to f at g of x, which means take the red function, g of x, substitute it into the black function, f of x, wherever there's an x. So that's why this red x squared plus f of x plus 6 has been put into this x for f of x. And we still have the plus 2 because that's part of f of x. And then we simplify it. The only thing we can do is collect the like terms, 6 and 2, which becomes 8. Now the other way around, g composite f of x. In this case, we want g at f of x. We need to take the function f of x, the red one, substitute it into g of x, the black one in this case, wherever there's an x. There are multiple x's. There are 2 x's in g of x, so you're going to be substituting f of x in twice. So it becomes x plus 2 all squared plus 5 times x plus 2 plus 6. Simplify, and our final answer is x squared plus 9x plus 20. Notice that f composite g is not equal to g composite f. So the composition of functions is not commutative. In other words, the order matters. With addition of functions, the order does not matter, just like addition of regular numbers. Same with multiplication. But with subtraction, division, or composition of functions, order does matter. Those operations for functions are not commutative, just like they are not commutative for regular real numbers. So let's go back to our challenge now. Oops, I lost it. Oh no, here it is. Good. Challenge 5 of 5. So the question was, using the composite function you found in the opening scenario, how could you solve for the time it took for the puddle to form and for the radius? So let's go back over here. And the function that we have is this one here, a of r of t equals pi over 4t squared. So how could we solve for the time, for example? If we were given the area, so let's look over here. We have an area of 19.63 units. We would simply substitute it in for a of r of t and isolate t, right? And if we wanted to know the radius, we would then have to take that time and put it into the r of t function for t. And then we can solve for the radius at that time. All right, so that is it for this video. Now I just have to find my tool that I was using to record it so I can turn it off. It's behind all of this stuff here. Here we go. Sayonara, guys.